Carbon nanotubes, CNT, are one-dimensional allotropes of carbon, consisting of a sp2 hybridized carbon lattice in the form of a cylinder. A single-wall CNT, SWCNT, the simplest version of a CNT, consists of a single cylindrical graphene tube. In double-wall CNTs and multi-wall CNTs, two or more tubes are either nested concentrically or wrapped like a scroll. SWCNTs are typically 0.4 to 2 nanometers in diameter, while MWCNTs can be much larger, with diameters of tens of nanometers, having both ends generally capped by fullerene-like domes. Similar to fullerenes and graphene, which are the analogous 0- and 2-dimensional allotropes of carbon, the graphite-like arrangement of carbon atoms in CNT and their shape give them remarkable and unique properties, which have resulted in the widespread use of CNT in several fields of science and technology, including energy storage, electronics, structural composites, biomaterials, and others. Because of their 1D structure, CNT exhibit highly anisotropic mechanical, electrical, and thermal properties, making them ideal for use in polymer, ceramic, and metal matrix composites. Additionally, their electrical properties, very high surface-to-volume ratio, and potential for chemical functionalization have led to their use in battery and supercapacitor components. The applications driving recent growth in CNT publications include energy storage, energy conversion, environmental remediation, CO2 reduction, and sensors. Battery applications were determined to have the comparatively highest level of commercial activity, based on analysis of journal versus patent publications. Furthermore, the growth of publications related to the synthesis of CNT appeared to slow around 2006, with a shift to more focus on solving challenges such as the optimization of the performance of CNT for specific applications, the use of CNT in emerging applications, and their combination with other nanoscale materials. The current era of CNT research began in 1991, when Sumio Iijima of Nippon Electrical Corporation's NEC Fundamental Research Laboratory in Tsukuba, Japan, synthesized MWCNTs using arc discharge evaporation from a carbon anode and characterized them with transmission electron microscopy. Subsequent research by groups at NEC and International Business Machines Corporation, IBM, in 1993 produced SWCNTs by incorporating a metal catalyst into the cathode. Chronologically, CNT were discovered between the isolation of fullerenes in 1985 and graphene in 2004. These include efforts to synthesize CNT using new methods or into alternate form factors, understand the properties of CNT through characterization and modeling, and evaluate and optimize their performance in various applications. Shortly after their discovery, theoretical studies provided valuable insights into the electronic properties of SWCNTs. By calculating the electronic structures of SWCNTs, these studies predicted that individual tubes could have either metallic or semiconducting electrical properties, depending on their chirality and diameter. Furthermore, they determined that Peierls distortion, which can interfere with the electrical conductivity of one-dimensional metals, was not a significant effect in metal like SWCNTs at ambient temperature. The theoretical predictions in these publications would later be confirmed by direct measurement of diameter and chirality using scanning tunneling microscopy, combined with measurement of the electrical properties of individual CNT. Building on this work, in 1998, research groups at Delft University of Technology and IBM fabricated CNT-based field effect transistors, FETs, placing individual SWNTs over a silicon-based gate structure between metallic electrodes, similar to a doped Si-based FET. Over the next 15 years, full logic circuits and eventually a computer were built using CNTs as the active components. During this time, researchers began using CNT in other applications that benefit from their 1D geometry, for example, using CNT as field emission electron sources. In 1998, CNT-tipped atomic force microscopy AFM probes were reported, demonstrating the potential of CNT in enhancing scanning probe microscopy capabilities owing to their inherent high aspect ratio geometry. An innovative example of this is the use of carboxyl groups present on partially oxidized ends of the CNT AFM tips as attachment points for other chemical moieties, thereby forming AFM probes that are sensitive to the chemical functionality present on a sample surface. The ability to explore the use of CNT in a wide variety of applications was enabled by advances in CNT synthesis in the 10 years following their discovery. In 1992, by optimizing the conditions of the arc discharge process, particularly the helium pressure, Ebison and Ajayan were able to generate and isolate gram-scale quantities of SWCNTs. Subsequently, a group at Rice University led by Richard Smalley developed a process based on laser ablation of metal/graphite composite targets to produce SWCNTs with high yield. Another major development around this time was the development of chemical vapor deposition, CVD, methods to synthesize CNT. In CVD, a carbon-containing precursor gas, benzene and acetylene in these early studies, flows over a substrate at elevated temperatures. Reactions between the precursor and the surface then lead to the growth of CNT from the surface. The degree of morphological control, adaptability, and scalability of CVD has led to it being the most common synthesis route for CNT today. An example of the control and scalability of CNT-CVD is the ability to generate aligned forests of CNT on a substrate consisting of catalytic iron nanoparticles embedded in silica. Smalley is perhaps better known for his work on developing the high-pressure carbon monoxide (HiPiCo) method of preparing SWCNTs, a type of CVD allowing large-scale 10 grams per day production of SWCNTs. Several methods are known for synthesizing CNT. In the arc discharge method used in the initial experiments in the early 1990s, a high DC current is passed between carbon electrodes, leading to carbon evaporation and the formation of SWCNTs. The first demonstration of controlled SWCNT synthesis also used arc discharge, with the inclusion of a transition metal catalyst. Later studies showed that ablating a carbon target using a high-powered laser could also be used to form CNTs. However, the most common method for the synthesis of CNTs over the last 2 decades is based on CVD, wherein passage of a carbon-containing precursor gas over a substrate in a reactor allows for reaction between the precursor and the surface, leading to gradual buildup of CNTs. The substrate can incorporate a catalyst, commonly nanoparticles made of iron, nickel, cobalt, or combinations of these metals, which can nucleate CNT growth and allow it to proceed at a lower temperature. A catalyst is generally not needed for SWCNT synthesis, but is needed to make SWCNTs, since the size and composition of the catalyst determines the initial stages of CNT growth, which determines the diameter and chirality of the final nanotube. The overwhelming prevalence of CVD can be attributed to advantages associated with it, such as scalability, industrial maturity of the technique, and adaptability and flexibility through the form factor of the reactor. An example of this adaptability is floating catalyst CVD, where catalyst particles are suspended in a stream of gas containing a hydrocarbon precursor, which decomposes and forms CNTs on the catalyst surface. The floating catalyst process can be adapted to generate a range of CNT macrostructures, including films, fibers, arrays, and sponges. In plasma-enhanced CVD, a plasma above the substrate is used to partially dissociate precursor molecules before surface reactions take place. This allows CVD to be achieved at lower temperatures, which allows better control of CNT properties in some cases. A significant challenge in CNT synthesis by CVD is achieving the required selectivity for chirality, diameter, and other structural parameters for a given application. The CVD process has several parameters that can be used to control structure, including the catalyst type, catalyst morphology, thin film, supported, nanoparticle, gas precursor composition, template, and reaction temperature. Applications of carbon nanotubes. Owing to the unique combination of material properties, CNTs are used in a wide variety of applications where they play critical functional roles. The largest fraction of CNT publications focused on their use in composites, including polymer matrix composites. The structure of CNTs gives them strength along their longest dimension, while their length allows them to act on macroscopic length scales. In addition, the ability to functionalize the exterior of CNTs either covalently or non-covalently can be used to make them compatible with a variety of materials. The electrical and thermal conductivity of CNTs allows them to act as functional components and not just as structural components. Composites are used in many products on both large and small scales. Their ubiquity and the useful characteristics of CNTs in them can account for their large fraction in CNT applications. Some of the applications for CNTs in composites include their use in batteries, in biocompatible hydrogels for heart cell growth, for use with a glycidyl polyketone to form non-conductive layers, to increase strength and wear resistance in composites with high-density polyethylene, to absorb high-frequency electromagnetic waves, and as components in heat-resistant aerogels. One caveat with the analysis of composites is that the term composite can refer to both a direct use of CNTs for their physical properties, i.e., structural composites, where CNTs are incorporated into a matrix to provide mechanical strength, or electrical or thermal conductivity, and a more general structure type in which CNTs are combined with other components, such as their use as catalyst supports. Classification as a composite thus may not exclude the use of CNTs in other applications. The largest fraction of patent publications on CNT applications was for use in batteries. The length of CNTs and their conductivity make them useful as molecular wires, and their strength could allow them to reduce the expansion and contraction of battery materials during charging-discharging, which leads to component separation and battery failure, or to form a barrier to dendrites, preventing short circuits and their associated hazards. These characteristics motivate the use of CNTs in batteries, such as with zinc oxide and carbon felt, in lithium-ion battery electrodes resistant to lithium dendrite formation, and materials such as graphene networks, nitrogen-doped carbon, and cobalt-iron metal-organic frameworks in biocompatible and hybrid zinc, or in zinc-air batteries. CNTs are also useful components for supercapacitors. Supercapacitors generally cannot store as much energy as batteries, but provide higher specific power, and thus enable power storage for applications not amenable to batteries. CNTs function in similar ways in both systems. Their high specific surface areas, conductivities, and electrochemical stabilities allow them to rapidly gather and transport charge. The significant fraction of publications discussing the use of CNTs in supercapacitors indicates interest both in supercapacitors and in CNTs. Sensors incorporating CNTs are a significant area of research, comparable to CNT/polymer composites. The strength and aspect ratio of CNTs enable them to transmit physical forces, while their electrical conductivity makes them useful for converting and transmitting stimuli. In addition, CNTs have a large specific surface area, increasing their susceptibility to external changes. A variety of sensors using CNTs have been assembled, such as a pressure sensor using conductive polymers, CNTs, and polydimethylsiloxane, PDMS, CNTs supported on polyurethane for use as a triboelectric generator, movement sensor, or chemosensor, with superhydrophobic surface as a flexible airflow sensor, in concert with nickel triphenylene complexes as a non-biological glucose sensor, and as nanoresistors to detect disinfectants. SWCNTs have been used in combination with samarium to detect solvent vapors, with polyaniline PANI to form ammonia-responsive materials, with epoxy resin to form a strain-sensing conductive material, and with polyurethane and polypyrrole to form a bendable pressure sensor. Other applications of CNTs make up significant fractions of the publication record. Biomedical uses of CNTs make up 12% of journal publications, though only 4% of patent publications. CNTs have been used as a reinforcing material for drug-delivering stents made with biocompatible polymers, as a conductive material with poly-3,4-ethylene-dioxythiophene, PDOT, used as a coating for nerve catheters, and as an antibacterial and structural material for bone implants. CNT have also been used as delivery vehicles for drug and gene moieties. While CNTs are readily functionalized, allowing their surface chemistry and charge to be altered appropriately for bioavailability, they can also exhibit toxicity depending on their purities, sizes, shapes, and whether they are integrated into macroscale forms, and may require dispersion or solubility in water. The properties necessary for the desired activities may lead to side effects, making them less commercializable. The safety of CNTs generally is an active area of research and policy debate. Besides sensors, CNTs have also been incorporated into other electronic materials, accounting for 8% and 9% of journal and patent publications, respectively. As noted earlier, the ability to functionalize CNTs to modify their electronic and chemical properties is important. The orientation and morphologies of CNTs can also be manipulated to achieve the desired device properties, but the manipulation of these properties is often manual and may require significant optimization to be produced on a larger scale. The relative amounts of patent and journal publications indicate that the benefits of CNT design likely outweigh impediments to their commercial uses. Some of the potential uses of CNTs include as components in FETs for instrument amplifiers, with bamboo-derived fibers, phenolic resins, and cobalt in a layered electrode material, and in a conductive fabric. Environmental remediation is a significant application for CNTs. The high surface area and conductivity of CNTs are important properties, as they make CNTs available for absorption and for mediating interactions with pollutants. The ability to modify CNTs allows them to be tailored for other co-catalysts or for reaction with pollutants. For example, lanthanum and iron-modified CNTs have been disclosed for environmental use, while a lanthanum gadolinium iron oxide perovskite reinforced with CNTs showed improved photocatalysis of the degradation of phenol red over the CNT-free perovskite. A CNT membrane was used to activate MnO2 for the oxidative degradation of water pollutants. Even though SWCNTs can conduct electrons well and have a high surface area, enabling improved reactivity and utility, their expense may make their use in environmental remediation difficult because the increased costs cannot be recovered by increased prices. Besides batteries, the use of CNTs in adhesives is the only other application with a high patent-to-journal ratio, which suggests considerable commercial interest in this area. The shape of CNTs could allow them to become entangled. Alternatively, functionalized nanotubes could react with surfaces with their strength, making them strongly adherent. For example, CNTs were used to reinforce PDMS dry adhesive pads. The CNTs improve the stability of the pads and diffuse concentration of charge at the PDMS surface, which leads to surface deformation and loss of conformity. Alternatively, a polyethylenamine (CNT) and epoxy resin material was used as an adhesive. Here, the nanotubes improve the strength-mass ratio of the material, while adhesion depends on the fraction of polyethylenamine used. Selected patents describe the use of CNTs for strengthening concrete and the use of a trans-stilbene/male imide polymer-modified CNT to make an adhesive with improved thermal conductivity. Thermal conductivity is commonly used in the context of using CNTs to improve the thermal properties of composite materials. Recently, these composite materials have included phase change materials, PCMS, which are used to store energy in the form of latent heat. In these materials, CNTs are incorporated with a bulk phase change material, such as paraffin, where the high thermal conductivity of the CNTs reduces the amount of time needed for the phase change material to take up and release thermal energy. A major advantage to using CNTs for this purpose is that they can improve thermal conductivity in phase change materials significantly at relatively low concentrations. In addition, CNTs are used in solar water evaporation devices, which convert seawater to fresh water, where low thermal conductivity is desirable to prevent heat loss through conduction. In these devices, CNTs are used primarily to take advantage of their high photothermal conversion efficiency. Recently, it has also been demonstrated that aligned CNTs can be incorporated into self-healing polymer matrices, providing high thermal conductivity to intrinsically self-healing materials. Both are critical properties in thermal interface materials used in high-power and dynamic devices. Research in triboelectric nanogenerators and thermoelectric generators is two other emerging applications of CNTs. Triboelectric nanogenerators are devices that can generate electrical energy from many different types of motion, including human motion or the motion of plant leaves in the wind. The origin of this electrical energy is charge separation that takes place during the mechanical interaction of two surfaces. In this application, CNTs are used to increase the surface charge density, thereby increasing the output power of the device. CNT-containing triboelectric nanogenerators have many possible applications, including self-powered sensors or providing power to wearable devices. Another application is the use of CNTs in flexible sensors and electronics. CNTs are used here primarily for their electrical properties, which can impart piezoresistive, piezocapacitive, and other properties useful for sensor applications. This can involve incorporating CNTs into matrices, including hydrogels, or combining them with polymers, for example, in a polyurethane/CNT yarn with hierarchical structure. Flexible sensors can also be fabricated by printing CNT containing ink onto flexible substrates. The major emerging application in these cases is monitoring human motion, either through wearable sensors or electronic skin. Another emerging application for CNTs is in the electrochemical reduction of CO2. This can be used as an approach for carbon capture that simultaneously generates a variety of useful chemical products. CNTs can be used in several ways related to catalyzing this process, including as a scaffold for supporting single-molecule metal-based catalysts, covalent organic frameworks, COFs, and pipette-like bismuth nanorods. CNTs, particularly when they are doped with nitrogen or other atoms, can also catalyze CO2 reduction, acting as metal-free electrocatalysts. Though with high potential, as with many other materials, the use of CNTs has been linked to health and safety concerns. More studies will be beneficial to further estimate the health and environmental risks as well as to develop preventive mechanisms along the way of advancing CNT-based nanotechnology. Among the diverse applications, the use of CNTs in batteries has a significantly higher commercial R&D activity in this area. Through these applications, the unique properties of CNTs, including strength, electrical and thermal conductivity, and ability for functionalization, are being leveraged to address the most critical problems and promising research areas currently known. Understanding the landscape of key emerging trends in this area, specifically the fast-growing applications, properties, and materials used in combination with CNTs, will be important for researchers who are driving further growth in the use of CNTs and nanoscale materials in general.